Hello, welcome at our webinar. So we'll wait for a few minutes before everyone joins. Welcome to everyone who is joining. We are waiting for a few minutes until all attendees join. So it's probably a couple minutes more. While at webinar, please feel free to ask questions. There is chat, there is a Q&A section where you can post your questions. So I'll be monitoring it and we'll try to answer right away, or maybe postpone till the end of the webinar. A couple more minutes. And please let me know if you can hear me well, or vice versa, if you cannot. Yes, good point. So someone has just pointed in Q&A that chat is deactivated. You're right, my mistake. Just you can post questions in Q&A section, and I'll answer it. Okay, I think we have more or less good number of people joined. So let's start our presentation. First of all, a little bit of a context and an introduction. My name is Oleg Chunikhin. And I apologize that I don't turn on my video. I have just recently broke my leg and I don't have good video setup where I'm right now, but won't prevent us from going through interesting use cases with Kubernetes and multi-cloud environments. Oleg Chunikhin, CTO at Kublr, have a long experience with various IT technologies, working with Kubernetes since its release. Feel free to message me directly if you have any questions after this presentation, or if you have questions about our company. Our company, Kublr, works and builds a product called Kublr, coincidentally, which is intended to provide IT operations teams in organizations and enterprises a tool that helps them manage multiple Kubernetes clusters in different environments. As such, so we help essentially companies, our customers implement this tool. We help our customers implement Kubernetes in general. And as such, we see that often an adoption curve for Kubernetes includes it's not so much good tool, it also requires good knowledge and understanding of the technology stack. Cloud native technology stack is quite vast and quite complex, so you need to understand what's there, principles of this stack, and even often just understanding what's possible with this stack poses a significant learning curve. So we helping our customers find use cases, interesting, closed, essentially situations where we can share this experience to a wider audience. And this presentation is one of examples of such cases. So where we want to show how you can use Kubernetes to create a cross-cloud, interconnected environment for your applications. So because when you have a single Kubernetes cluster, clearly it creates a well-defined network space for your applications. So if you're familiar with Kubernetes, you probably know this terminology. Nodes are physical or virtual machines where Kubernetes can run containers. Each node usually has its own IP address, or maybe multiple IP address in more complex cases, but we'll talk about a simpler case where each node has just a single IP address. And so on that level, those nodes represent physical network. So you can SSH, for example, into each of those nodes and then connect to other nodes from there using those physical addresses. Kubernetes, on top of that physical network, builds a so-called overlay network. It's usually so multiple Kubernetes components involved into this process. Kublr, which is a Kubernetes agent which runs on every worker node. Kubeproxy, responsible for IP tables or NF tables configurations. CNI plugins, responsible for tunneling or routing or any other ways. So, and CNI plugin is usually the most important. My apologies. Very good comment. Andrei says that you cannot see slides. I must check. So that now you should see the slide where I'm talking about Kubernetes networking. So I talked about physical network, and now I'm talking about virtual network, overlay network that Kubernetes creates on top of this network. Usually overlay network has a different address range than the physical network. So they are not intersecting. This helps separate physical resources and resources that use network inside of the Kubernetes network. Every pod that you run inside of your Kubernetes cluster, and for the purposes of this presentation, those pods will use pod and container terminology interchangeably. Every pod gets its own IP address inside of this overlay network. On top of that, Kubernetes also allows you to use so-called services. So services is a virtual object, so to say, something that only exists virtually and is usually implemented using IP tables or MF tables. So it's a stable IP address connecting to which Kubernetes will forward your connections to one of the pods underlying the services. And the set of those pods underlying the service is dynamic. So essentially pods can start, restart, come and go, and Kubernetes will dynamically rebalance, reconfigure this virtual service IP address so that connections to it will go to only active and live pods. And on top of this, there is a service discovery layer. So Kubernetes cluster gives you a way to access those services and pods by DNS names. So this is how a single Kubernetes cluster looks like from network perspective. Now, what if you want to connect two clusters? What if you have two different Kubernetes clusters running in different regions, clouds, data centers? So what does it take to connect them physically over the network? Well, normally you would want probably physical connectivity so that you can connect to physical nodes from one cluster to another cluster and vice versa. You would want to be able to send through pod connectivity and services connectivity so that addresses in this overlay network in one cluster are accessible from the other cluster and vice versa. And you would want to enable DNS forwarding to essentially make sure that names of services and pods in one cluster are accessible from the other cluster and vice versa. And the only way to achieve all three is to make sure that address spaces of all these three layers are not intersecting. So the only way to achieve this connectivity in this way, as I described, when every layer is accessible in the other cluster, is to make sure that, well, physical addresses are non-intersecting, use non-intersecting ranges. Overlay addresses use non-intersecting ranges, and the DNS space of intra-cluster DNS network is non-intersecting, uses different domains. It's possible, but it requires preliminary planning. So when you deploy your cluster, you will specify which physical network it will be using, which overlay network range it will be using, and which DNS domain it will be using. Alternative approach, if you have two clusters where those ranges are already intersecting and you cannot change that, the only way to provide connectivity is through some common shared space, so to say. When you specify a range of addresses that are not intersecting with any of those clusters, and you expose some of the services inside of each of the clusters inside of this space, and then you expose this space to each of those clusters. Now, both strategies work. The first one is sort of a little bit more transparent, requires less hands-on, but provides more visibility between clusters. The second requires more work in terms of specifying which services to which clusters need to be exposed. Depends on specific application that you want to implement. Now, in this presentation, in this webinar and the demo, I wanted to show you how Submariner works. Submariner is essentially a specialized VPN solution for Kubernetes clusters that enables you to establish both of these previously described strategies. So Submariner is a Kubernetes application first and foremost. So you run Submariner component in each of the clusters, components in each of the clusters that you want to connect. And you still need to be aware of, or make Submariner aware of how you want this cluster to connect, where the entry points can be established in each of those clusters, so that Submariner running in each of those clusters can establish peer-to-peer connections. But that's the only thing that you need to do. The rest, Submariner does itself. So it does synchronization, orchestration through this peer connection, etc., etc. Submariner exchanges, Submariner components exchange data and state of each of the connected clusters through a Kubernetes namespace. And that namespace can be anything. It can even be in a third cluster somewhere else. So you just give Submariner access to some Kubernetes API endpoint and tell that it can use that namespace to exchange meta information for your connected network. In our example, this namespace will be in one of the connected clusters. So Submariner allows both service discovery strategies that I described in the first slides. So after establishing the first overlay level network connectivity and physical network connectivity, if necessary and possible, it also plugs into Kubernetes DNS layer and establishes DNS forwarding. Main components of Submariner include broker, which is essentially that namespace where information about connected peers is stored. So it's not an active component, it's just a storage of metadata. Gateway engine, that's essentially a set of components that represent VPN gateway inside of each peer clusters. And service discovery component, the one that controls exposure and export and import of services between different clusters. So before talking about specific details of Submariner implementation, let's see our experimental setup. So first thing first, I used Kublr to create two Kubernetes clusters. One in AWS cluster has a couple of worker nodes, a single master. Another cluster runs in Azure, similar structure. So, and by the way, you can follow this demo based on our GitHub project, GitHub at Kublr Submariner demo. So you can just go through this README file. Moreover, this whole demo is essentially a process of going through this README. So the first step that we did, we created two Kubernetes clusters, and I configured their config file in my local environment here in my command line, so that I can now verify that I can access each of those clusters using kubectl. Let's see. Okay, so as you can see, when I use the first kubeconfig file, I can see my AWS cluster nodes. When I use my second kubeconfig file, I can see my Azure cluster nodes. So, and we already included Submariner components, deployment of Submariner components, or at least prerequisites for Submariner components into these cluster specifications. So with Kublr, when you deploy a cluster, you can either use this graphical UI where you specify where you want to deploy your cluster and how many masters you want to have, how many workers you want to have, and then just click confirm and install so that your cluster gets created. Or alternatively, you can use Kublr API, or you can use just this dialog where you would submit this quite large YAML document which describes this cluster configuration. So our GitHub project includes configurations for those two clusters so that you don't have to compose them again. So we can check this cluster's configuration structure. So it's Kubernetes 120. In addition to standard configuration, you can see that we included some additional ports opened in those clusters. So you can see that in this Kublr cluster specification, AWS specific resources, additional security group ingress rules included that allow those VPN connections. We specify here that it's a mixed instance policy cluster which uses spot instances so that we don't have to spend too much money on a demo cluster. And here you can see that we configure these clusters IP ranges and whatnot. So everything that is necessary for the first connectivity strategy to work so that we don't have intersecting address ranges. And there are a number of other customizations. So most important to understand the structure of this cluster specification is to see how it's structured from Kublr standpoint. So we have metadata part in this cluster, cluster name, etc., etc. We have cluster-wide non-provider specific configuration, like which Kubernetes API port to use, for example. We have infrastructure-specific provider cluster-wide configuration, where we, for example, specify those additional AWS ingress rules, etc., etc. And then for each node group, whether it's master or worker, we similarly have non-provider specific and provider specific parameters. Apologies. And additionally, we include in this specification additional software packages. We can see it here, for example. So in this cluster, we include additional resources deployed as Helm packages that prepare this cluster for Submariner. And you will notice that it includes a Submariner Helm chart and another Helm chart that just deploys a job that tags certain nodes as gateways. So that may seem complicated, but it's intended to make essentially management of all those details easy. So in the end, figuring it out once and putting, for example, this cluster spec in your Git repository, you can recreate those clusters and literally in minutes, hiding all that complexity and letting Kublr or other Kubernetes management solution to manage it. So let's get back to our demo. I already configured those kubeconfig files for each of those clusters, and I already have Submariner installed on my machine. So the next step is to actually prepare certain Submariner common Submariner parameters that we need to establish trust between those two clusters. So it's as you can see here, it's just a set of environment variables that I will configure. Some of them just initialize shared keys. So here they are. So we put a name of this broker namespace into an environment variable. We prepare a pre-shared key for VPN to be secure. We extract Submariner broker certificate authority, token, URL of the server where this broker namespace is stored, is located, etc., etc. So now we have all those environment variables initialized. And the first thing is we connect the first cluster. As you can see here, we define some parameters for the first cluster we will bring into the peering, and we use Helm to deploy a Submariner operator with those parameters. And the first cluster we connect is AWS cluster. So Helm takes some time to provision a Submariner operator in our AWS cluster. And second, clearly, is adding Azure cluster into the picture. So again, remember that Submariner has 3 components. We initialized broker namespace as a part of the Kubernetes clusters deployment. And now we deployed Submariner operator active components into each of the peer clusters. So, and the next step, now we can just check the status of the peering connectivity between those clusters. Okay, we can see that Submariner already sees some of those components, but no peering connection is yet initialized. Takes some time. Now on the second request, we see that, hey, checking our Azure cluster, we see that Azure cluster connected to AWS cluster, and everything seems to be normal. So all connections are established and on all levels. And now we can test how it really works. So to test it, first and foremost, I will deploy a set of test pods. So I will use a daemon set, which means that on each node of the cluster, a pod will be started. And this pod is using Quay gravitational netbox image. So netbox image is essentially an image which includes a number of network utilities that we will use to check connectivity. And in reality, I will I will run 2 sets of pods. One is a daemon set named test-SRV host, and another is test-SRV pod. So we will use them for different types of tests. So let's do that. And it's a script which deploys exactly same sets of pods and daemon sets in each of the clusters. Also, you see that we create a service for a set of our pods to verify that connectivity to services is also working. Okay, now let's see statuses of our pods. Okay, here we are. Some of them are already running in some of the in AWS clusters. In the AWS cluster, they are already running. In Azure, they are still creating. Let's see. Okay, now all of them are running. Let's clear the field, and now we can test that connectivity works between all the pods. So this quite a long command does actually a simple thing. So iterating between both clusters and iterating through all of the pods in each clusters. It checks that we can connect from each pod in one cluster to each pod in another cluster. And we just print the result of this connection. And by connecting, I just mean running curl inside of one of the pods to the other. Let's run this command and see how it works. Looks like so far so good. So we can see that connectivity from AWS cluster pods to AWS and Azure cluster pods is correct and works. So now we at least know that when we use IP addresses of pods in one cluster, in pods in another cluster, connectivity works. Similarly, we can test connectivity from pods to services between clusters and inside of the cluster. It looks like that works as well. Now here we used IP addresses for services. The next layer test is DNS names. Here you can see that we are running connectivity from pods to DNS names, and you can see that being in AWS, for example, we test connections to cluster 1 local. Being in Azure, we test connections to cluster 1 local, and vice versa. From both AWS and Azure, we test connections to cluster 2 local, which is the mains in those different clusters. So we can see that DNS forwarding works as well. So the last test is this approach where you use common service area and you expose services in one cluster to another cluster one by one. So with Submariner, it is done using a special type of object called service expert. So you essentially create this type of object, service expert with the name of that service that you want to expose. And picking that up, Submariner operator actually creates a service object that represents this exported service inside of your cluster. Okay, so now we can see that this service expert object was created. We can check its status. We can see more information about it, or even its YAML format. So you can see that right now it shows that there are two conditions that allow you to assess whether the export was successful, and there is a condition named let me see. So now it tells us that condition of type valid has status true, saying that service was successfully exported, which probably means that we can now test it. So let's verify that we indeed can connect from both clusters to this virtual service created by Submariner operator. You will notice that unlike Kubernetes native services, these services created in a virtual namespace have their own domain set. So while Amazon cluster has DNS domain cluster1.local, Azure cluster has DNS domain cluster2.local. This virtual Submariner namespace has a domain name cluster set local, and there you put your shared services. So we can see how it works. Just to summarize what we achieved, we relatively quickly put 2 clusters out there in 2 completely different clouds. They don't have to be Amazon or Azure. They may be your 2 different regions in the same cloud. For example, your AWS East Coast and your AWS West Coast clusters, where you want to set up an application in a failover mode, or maybe your data center and your cloud expansion. They can be symmetrical and run active components of your application, or they may be asymmetrical, for example, where you run core components of your data science team software in the data center, but expand into the cloud when you need more resources. So the use cases are limitless, literally. And Submariner as a tool setting up VPN connectivity between those separate disconnected clusters, and Kublr as your infrastructure as code, essentially framework that allows you to formalize all those definitions and put them into a single comprehensible specification, allow you to very quickly set up and reset or migrate those environments, define those environments and manage them. So what we didn't cover in this demo. So there are, of course, a number of questions that are related, tangential, and but also interesting, but we didn't have enough time in a single presentation to talk about, is how that all can be optimized. Of course, every distributed system needs to think about various compromises, and usually cross location connectivity is slower than intra-location connectivity. This is often also related to application architecture questions, how your application works, and what are throughput requirements for application, for example. For your application, it's a lot of interesting topics for discussion. This demo doesn't really show you how Submariner works in a situation where your clusters have intersecting CIDRs or address spaces. So we set up a simpler case where on all layers we have non-intersecting CIDRs. When you have intersecting CIDRs, as I said, it requires a little bit more planning and understanding which parts of your network space you want to expose from one cluster to another and vice versa. So failover and load balancing. While by default we deployed this Submariner setup in failover mode. So we didn't demonstrate how Submariner recovers from failures. But just you can believe me or read it in Submariner documentation. You can easily set up, and this is a default setup, multiple gateways, gateway nodes for Submariner. So if one gateway node goes down and connectivity went through that node at that moment, Submariner will automatically switch to a different gateway node. So after a short disconnect, connectivity will be recovered. CNI support and integration is also an interesting topic. So Kublr uses Canal CNI plugin by default and allows you to use Viv, Calico, Flannel, but also pretty much any other CNI plugin. Submariner has its own requirements, so that with different CNI plugins, setting Submariner up may be a little bit different. So there are a number of interesting topics to discuss about that. And that actually relates to one of the questions I can see in our Q&A section from Tony. So how does Submariner compare with other multi-cluster networking approaches like Cilium and Traffic? Well, it is related in that Submariner allows you to establish this connectivity. It does it differently than other approaches. So Cilium is in itself can serve a CNI plugin inside a single Kubernetes cluster, and having two Kubernetes cluster with Cilium CNI plugins, you can connect them almost exactly in the same way as we just did using Submariner. But it's sort of specific to Cilium. You either have to have Cilium configured the right way in both clusters or in all your clusters, or you have to figure out, if you are using a different CNI plugin, you have to figure out how to correctly pair Cilium with non-Cilium clusters, essentially. It's possible, but it's a non-direct thing. Submariner separates this function of VPN and cross-cluster connectivity into in its own function set. So Submariner works on top of pretty much any CNI plugin. So just requires that your cluster has intra-cluster connectivity configured in a more or less generic way, and then it will connect. It will allow you to connect to cluster irrespective of which CNI plugins they are using to provide intra-cluster connectivity. Clearly, there are pros and cons of each approach. By the way, some other CNI plugins can also be used to set up cross-cluster connectivity with some limitations, like Calico, for example, can allow you to establish BGP-based, routing-based cross-cluster connectivity, as long as you can establish physical connectivity on some level between clusters. Traffic is a different beast. Traffic does similar things or allows to do similar things on application level. And similarly, similar approach is used by Istio, for example, and generally speaking, service meshes. So you can use different service meshes in your different clusters. Those clusters don't need to be connected in any way on their network level, but service meshes running in them have endpoints exposed, and through those endpoints, they can connect just like any applications running in separate clusters and using that connectivity, so they can establish peering and mesh across multiple clusters on the service mesh level. So hope that answers the question, even maybe though a bit longish answer. Okay. I put a few useful references in the presentation. This presentation is available on our website, and video of this presentation is available or will be available on our website. Now I think if there are a few questions, I'll wait for a minute for more questions as they come. And if not, thank you for joining this presentation again, and thank you for your interest. Feel free to mail me directly or message me directly on Twitter or email. Happy to have you here. Okay, thank you all. This concludes our presentation. Bye-bye.